Okay, so hey everybody. Hopefully I am actually making a video here. So I'm in a Zoom conference with just myself, and it's a little bit lonely, but I'll get through. Okay, so what I'm doing today is trying to create a brief video that talks about pipes. And so um, I'm still having some laptop slash networking problem where I'm unable to push my web pages up to Clemson's site, and I don't know why. But we'll be able to look at the correct material on my laptop, and I'll fix the website problem um, within a couple hours after class today. So when you what you will see once it's fixed is, so today is 3/27. There's this web page that we've had for a number of years that's I use all the time. It's super handy to verify if we're having network issues or connectivity issues. So if you click it, you would go to a site called cybertiger.clemson.edu and click on web apps, click on PHP bandwidth test, and then basically this uses Node, which is a web networking server actually that makes it pretty easy to do networking on a remote system using HTML. So typically what I do is I say both. That means both directions. We're going to get an estimate of the throughput in the downstream direction. So a download would be from Clemson to my laptop, and then the upload direction would be from my laptop to Clemson. And on the right-hand side, you should see something that looks larger than zeros, okay? And so one of the things that I'm worried about with the class all remote and you're all using Zoom is if any of you are having network issues. So for example, I think the Clemson's VPN endpoint, or they have a gateway machine, is overloaded. So I see high packet loss, and I basically cannot maintain a VPN for more than 2 minutes. But connectivity, when I don't use the VPN, is good. And so I'm not sure if any of you are having problems with that at all. So this tool is, you could use this to see what your um, download speeds might be and upload speeds might be. All right, and so now homework 3 is out, so I'm going to go through that in this short video, and we're going to step through this PDF that introduces pipes, and then I've already prepared the sort of after lecture class lecture notes. So let's actually look at the lecture notes. Let's start with that. Okay, so today, talking about today's class, I created the video I'm creating right now, which probably won't be online in time for class, but I'll be able to point you to it. And so in this is a summary of basically what we're going to be talking through. And so I'll start out here saying that the big topic is interprocess communications. And so that means how can applications running on the same host communicate? And there's multiple ways. One way is by a file, and probably you all have done this at some point in time. You have two programs running and they need to exchange data. An easy way to do it is have a writer. So one of the programs write to the file and then the other program read. And as long as you just are aware of the timing issues that might happen. So if both programs attempt to write at the same time, the file data might get messed up. Typically, you would get a F lock, so a file lock, before reading or writing to ensure the critical region is not compromised. As a review with the Unix IO system, it's based on a stream, okay? And so when we do an fopen of a file, we are returned a handle or a pointer to file star. So that is called a stream. And think of that as it's access to the file contents through middleware, where the middleware would be, all of the library calls that allow you to do character by character input output, or line by line input output, or block input output. At the layer below the stream, its bottom end is interacting with the core Unix IO file system. And so there it is doing reads and writes. And so let's see if I have the syntax for a write operation. We could go to my VM. And if we do a man of write, so we see that, okay, this is not the right man page. Apropos, one of my favorite commands, is basically like Google on Unix. So we want to find out information about write. This tells us all the different things that we could look at. So it's telling us that there's two man pages on write. So we want to specify section 2 rather than section 1, man to write. Okay, so this is write. It uses a file descriptor and a pointer to a buffer and a number of bytes. So it's not as functional as the stream interface. The underlying file system does actually support lseek, which means that when it's maintaining sort of the pointer or the octet actually at which you're currently at in accessing a file. But this IO abstraction of read and write using just a file descriptor is not just for files. It could be how we access devices. It could be how we access sockets. Okay, and so this gets us back to the point that I made in the lecture notes, thought question 1. So, all right, so we're talking about IPC. What if we were to run UDP Echo version 3, our UDP client server, on the same host? Okay, so is a socket, a network socket, a form of IPC? And we'll get to that in a second. All right, so final thing I wanted to point out or remind you all of related to file I/O. All right, so normally we are accessing files using a stream. If we ever needed this file descriptor, we can get the file descriptor from a stream handle with the file no system call. All right, another form of IPC is pipes, which is what we're going to be talking about. Shared memory is another form, and that's actually the most efficient in terms of, efficiency is typically measured as the bytes per second that we can transfer from one process to another, and shared memory would be the fastest. Okay, so the thought question I asked of, is a network socket a form of IPC? It actually is. So something that is sort of like a socket, but not quite. So another form of IPC is called a Unix domain socket. It looks and smells just like a socket. Okay, we would specify pf_local rather than pf_inet, right? And that was where we're specifying IPv4 or IPv6. So pf_local is Unix domains, but it basically gives us a socket descriptor, and we can do sends and receives. So the final answer to the question of, compare all of these mechanisms to a network socket for IPC. We could use a network socket, and we would use the server name of localhost. It's not as efficient as the other mechanisms. Okay, so as we continue here, there's new stuff in JIT. So issue a JIT update, look at code, and what we're going to talk about today is IPC pipe concepts. You'll also see in code TCP Echo and TCP Echo version 2, and we'll talk about that when we hit the homework discussion. But this video will focus on pipes. Okay. So back to, so the current web page is more or less up to date with a couple of links missing. Okay, and my starting point for talking about pipes exists already on the web page. So it's the overview of Unix pipes. Just a short set of slides. So this tries to basically show with a picture what I just went through, demonstrating different types of interprocess communication. So if two processes use a file, it might look like this. If this second method here, two processes using shared info, that maps to a pipe, okay, which is what we're going to spend most of our time on. So the pipe is actually a data structure that is managed by the kernel. And we won't get into the details of how it does that, but logically, this is what the picture looks like. This third little visual here is showing shared memory. So it's possible to have the shared memory at user space, which is really why it is the most efficient. It eliminates the need for bouncing back and forth from user space and kernel space. All right, Linux supports half duplex pipes. It does not support full duplex pipes. There is such a thing as a full duplex pipes. BSD, Unix, like FreeBSD supports full duplex pipes. So if we need full duplex, so if we have two processes that need to talk, send and receive with each other, all we have to do is set up two pipes. And that gets around not having a single pipe that can be used for both sending and receiving by both sides. Okay, the difference between a pipe and a FIFO, we need to talk about related processes and unrelated processes. When a program and a main process forks a child process, those two processes are related. If that child process forks other children, they're all related to the parent. And so they can use pipes to communicate. If we have two programs that are running, two instances of a program, it can even be the same program. So two instances of the same program, they cannot create pipes. Instead, they would use something called a named pipe or a FIFO. And it's pretty easy to understand the difference. We'll see that shortly. Okay, moving on. So when we look at the code that's in IPC in that directory, we'll get into this a little bit more. We want to have some understanding of how the shell, what the shell is doing when it's running programs, and how it's using pipes. So this first line here, who piped to sort, piped to word count. So that vertical bar represents a pipe. And just at a high level, what bash, the shell program, is doing is it's parsing the input and it's looking for vocabulary and language and syntax that it understands. And so it determines that, okay, this is a program and its output needs to be piped to the input of this program, whose output needs to be piped into the input of this program, whose output would go to standard out. Okay, so bash would fork three child processes, one to run who, one to run sort, one-to-run word count. And it would create, it would create a pipe. In fact, it would create 2 pipes. So there's a system call called pipe. And these bullets here show the system call pipe, and the parameter is going to be a pointer to an array that will hold 2 file descriptors. Okay, one would be for the reading and one would be for the writing of that pipe. We fork a child process, and we're running within the context of the child process. So this magical call dupe2, we'll look at this in a bit more detail. It it redirects the output from this process so FD0, 0 is going to be standard out, and we're replacing the standard in of this process with the standard out from the parent process. And again, we'll look at code that makes that a little bit easier to understand. Okay, so this sort of talks about the same thing. The parent creates a pipe and a child process. We're going to say that in this example, it's actually not quite doing this. Okay, so in this example, it's simpler. The parent just wants to be able to talk to the child through a pipe. So let's see, the FD0 is the standard in of the process. FD1 is the standard out. So the parent's standard out goes to the pipe, and the child's standard out goes to the pipe. The output of the pipe goes to the parent's standard in, and the output of the pipe goes to the child's standard in. And so the child, when it reads, it's actually going to read data that's coming from the standard out of the parent. Okay, and this is an application that's in our code that we'll be looking at. So I'll give a brief overview of it. So here, again, we create the array that is used to hold the 2 descriptors. So 0 is going to be for the reader, 1 is going to be for the writer. This is the system call that will create the pipe, and it will, when it's done, it's going to have filled in the 2 entries of this array will be the read descriptor and the write descriptor. We do a fork. If CPID is 0, that means this is the child process. So we're going to close the pipe, which is the writer, because the child is just going to be the reader. And it goes into a loop reading from the pipe. and then it writes to standard out what it has read. And then it figures out when it's done and terminates. The parent, so it's just doing the writing, so it's not a reader. So therefore it can close the read descriptor. It's going to write to the pipe. I believe this program takes a argument like a string. So we just type in something and the parent is going to send it to the child over the pipe. So we write to the write descriptor of the pipe and that's it. Then we close the pipe. Okay, full duplex. So as I said, we could create 2 pipes, and not going to go into details with this. There's a, just like the dupe2 call is very helpful in terms of it does things for us that our code would have to do if we didn't use dupe2. There's a system call called popen, which does, which is extremely useful for forking a child and setting up a pipe. And we'll see more of that. Well, actually, we're not going to look at that code. So this will be all the popen code that we'll be looking at. So this is just as an example. Okay, so this code is basically going to invoke a command, and it's going to cat a file name. Okay, and so how we've talked about this before is the parent would fork a child, the child process would exec the cat program, and a pipe would be set up where the parent is able to pass the file name to the child, and then the child does the cat and it uses standard out. Okay, instead of that, there's a single command popen that does that for us. Popen command would be cat files. So, and then all we need to do is it returns a effectively the pipe, and so the popen does the fork and the pipe setup for us. And after we run popen, so the child is running, doing its thing, and the parent process is going to read from the child process. Okay, so in this program, the child process is going to do a cat of the file name, and the output, instead of going to standard out, is going to go to standard in of the parent process. Okay, so named pipes. So it's all very similar to pipes. The exception is, or the difference is, that the pipe has a, instead of using the pipe command, we use other commands that create a FIFO. So it's make FIFO is the command. So with pipes, there was no name associated with the pipe. Okay, with a named pipe, there is a name. So make FIFO, we have to give it the name of the pipe. So here we're creating 2 FIFOs, two named pipes, one called FIFO1, one called FIFO2. And the parent forks a child that opens FIFO1 and FIFO2 for read-only. So FIFO1 is read-only, FIFO2 is write-only. The child then calls the program that it's running. So the concept is identical, and so when a FIFO is created, there again is a pair of file descriptors that are created, and so there's one for sending and one for reading and one for writing. And if we were to actually look on the file system, we would see a file called FIFO1 and a FIFO2. And when we look at the code, we'll see more of this. So the advantage of named pipes is it works with unrelated processes. So as long as two applications running on the same host know the name of the pipe, like FIFO1, and they each have access to, or they're allowed access to the pipe, they can use the pipe to communicate. Okay. All right, so let me briefly go through homework 3. Actually, I think I'll sort of end this video now because our real class time is coming up, and I'll post this video along with the video of today's class. And so today's class will, I'll refer to this video for the things that we've talked about so I don't repeat myself, and we'll probably go straight to the JIT code example. Okay, so with that, I'm going to sign off.